In this lecture, we are going to see in detail about conduction. In last lecture, we have seen modes of conductions like conduction, modes of convection, forced convection, and natural convection, and what is radiation, and their respective laws like Fourier's law for conduction, Newton's law of cooling for convection, and Stephen-Boltzmann law for radiation. So in this lecture, what we are up to is we will see in detail how conduction is being studied, the detailed analysis of it. In the detailed analysis, we need to consider a cube of size dx, dy and dz. Dx is the size of cube in x direction. You can see directions here, x, y and z. So qx is amount of heat flowing into the block in x direction. Qx plus dx is amount of heat flowing out of the box in x direction. Similarly, there is qy in y direction flowing in, and qy plus dy is flowing out of the cube. Qz is heat flowing in z direction, as you can see from the bottom of the cube, and qz plus dz is amount of heat flowing out of the cube. So this is the structure of a cube dx, dy, dz to study three-dimensional heat conduction equation. To form energy balance, we can write energy flowing inside the cube minus energy flowing outside the cube plus amount of heat generated internally is equal to energy stored. Now, what is this energy flowing in qx, qy, qz? Energy flowing out qx plus dx, qx plus y plus dy, qz plus dz. And now what is this energy generated? Energy generated is because of the nature of the material. You can see the note here. The medium through which heat is conducted may involve the conversion of electrical, nuclear or chemical energy into heat or thermal energy. In heat conduction analysis, such conversion process are characterized as heat generation. Means what? Due to the electrical flow or electrons flow, or there may be certain nuclear energy flow or chemical changes due to heat flow that causes internal energy to generate. So that is been added to energy inside the block, and which is equated to energy stored. Energy stored is the amount of energy stored inside the cube. So the same equation we have written here, energy in minus energy out plus energy generated is equal to energy stored. So in mathematical form, it is something like this. Energy in is qx plus qy plus qz. Energy out is qx plus dx, qy plus dy, qz plus dz, which has been subtracted from energy in, and then added energy generated, which is nothing but qg into dx, dy, dz. Now what is qg? Here you can see where qg is heat generated per unit volume. So if qg is heat generated per unit volume, what we have done is we have multiplied it with total volume of the cube, which is dx, dy, dz. So this will give you total energy generated inside the cube, and then energy stored, RHS part of the equation, which is nothing but rho is density into dx, dy, dz is volume. Density into volume is m, mass, into Cp is specific heat of material, and then T by T. Now this T by T is change in temperature with respect to change in time. So this equation gives us total energy balance of the cube. So from this equation, what we can do is we can write qx plus dx. Now this qx plus dx, it can be expanded in the form qx plus dabba by dabba x of qx into dx. Similarly, qy plus dy is equal to qy plus dv by dy of qy dy. Qz plus dz is equal to qz plus dv by dz of qz dz. Neglecting higher order terms, we can substitute these values in above equation. So what was the equation? This was the equation. This is qx plus dx, qy plus dy, and qz plus dz. In place of these 3, 1, 2 and 3, what we are going to do is we are going to substitute these new values of the respective ones. So when we are substituting these values, you can see this qx, this qy, this qz. When it will be substituted here in this bracket, what will happen? This qx, qy, qz will get cancelled with the new qx, qy, qz, because it is positive, that is negative, and hence what remains inside is negative sign outside the block. Then what remains is dv by dx of qx dx plus dv by dy of qy dy plus dv by dz of qz dz. So this is what remains for energy in minus energy out. All the remaining parts like energy generated qg dx dy dz and energy stored, that is rho dx dy dz cp dv t by dv t, will remain as it is. So when we have got this equation, what we can do is we can replace this qx, qy, qz by using Fourier equation. Now what Fourier equation says is this: qx is equal to minus kx ax dv t by dv x. Now what is this kx ax? Kx is thermal conductivity in x direction, ax is area through which heat is passing in x direction, and dv by dv x of t is nothing but this is tangent temperature with respect to length. So this is Fourier's law, or we can say Fourier's equation. So this equation for x, similarly for qy, and similarly for qz, what we can do is we can substitute it. Now this ax, ay and az are the areas. Areas are ax area is dy dz, ay area is dz dx, az area is dx dy. These areas are nothing but areas normal to the direction. In x direction, what planes come normal to it is dy dz. So that is why area is dy dz. So that is how we are going to substitute the values in above equation. So the equation is briefly written here again in small font. So this qx will be replaced by Fourier's equation. This will be qy will be replaced by Fourier's equation, and qz will be again replaced by Fourier equation. So what remains is dv by dv x of kx dv t by dv x plus dv by dv y of ky dv t by dv y plus dv by dv z of kz dv t dv z. All remaining parts are same. Here you can see the difference. The term dx dy dz and on RHS dx dy dz is cancelled. How it is cancelled? Here, while placing value of qx or qy or qz, what happens is, let us consider this first term. Here dx is already there, and what we are doing is we are putting in the value of area. So what happens is this dx into dy dz. So dx dy dz is a term in first qx value, then in second there is qy. So what happens is to qy is dy is there and area comes dx dz. So again it becomes dx dy dz. In third term also, in place of qz, what we can have is dz is already there and area is dx dy. So in all these terms, dx dy dz, dx dy dz and dx dy dz, they become common. So we take them outside and divide the whole equation with dx dy dz. So what remains is from RHS only dv by dv x of kx dv t by dv x plus dv by dv y of ky dv t by dv y plus dv by dv z of kz dv t by dv z plus qg is equal to rho cp dv t by dv t. This equation is the general form of heat diffusion equation in Cartesian coordinates. This is for time dependent. Time dependent means we have considered this t by t term, which indicates that temperature may change with respect to time, and hence it is unsteady state heat conduction with variable thermal conductivity. Variable thermal conductivity means in x direction we have considered kx as thermal conductivity, in y direction we have considered ky as thermal conductivity, and in z direction we have considered kz as thermal conductivity. So variable thermal conductivity is also considered in this equation, and uniform heat generation within the body. Uniform heat generation is indicated by Qg. So this is the general form of heat diffusion equation. So this is what we have derived in three-dimensional heat conduction equation. To simplify it, what we will consider is, if we consider or assume the material is isotropic. So if material is isotropic, the properties will be same in all directions. So Kx is equal to Ky is equal to Kz is equal to K. So when K is constant, thermal conductivity constant, what we can do is we can write the equation like this, and then instead of Kx we can write K, instead of Ky we can write K, and instead of Kz we can write K. We can take out this K common and divide the whole equation by K. So dividing both sides by K, we are going to get a new equation something like this, which shows the first part dabba square by dabba x square of t plus dabba square by dabba y square of t plus dabba square by dabba z square of t is equal to Qg divided by K is equal to rho Cp by K into dabba t by dabba t. Here this equation is a simplified one for isotropic material. So what we can do is, here we can replace this term rho Cp by K by a new term called as 1 upon alpha. So the equation we can write down for this first three terms on LHS, we can take it as a Laplacian operator, which is indicated by grad, the sign grad. So what we can do, because it is in the square format, what we can do is grad square t. For this first three terms, dabba 2t by dabba x square plus dabba 2t by dabba y square plus dabba 2t by dabba z square, we are replaced with Laplacian operator, which is grad. So grad 2t plus Qg by K as it is equal to 1 upon alpha dabba t by dabba t. This alpha is nothing but the thermal diffusivity. This thermal diffusivity is actually K upon rho Cp. We will see the term in next lecture. So right now this equation is a concise format of three-dimensional heat equation in Cartesian coordinates. Now let us see how we can simplify this equation, or we can see more special cases of this equation. So first special case, when the equation is applied where conditions are steady, that means steady state conditions. So in steady state conditions, what is the basic consideration? Basic consideration is temperature or properties never change with respect to time. They remain the same throughout the time, and hence we can write dabba t by dabba t is equal to 0. So equation becomes grad 2t plus Qg by K is equal to 0. Right hand side becomes 0, and this equation is known as Poisson's equation, important equation for steady state. It is Poisson's equation. Next special case is where there is no internal heat generation. With no internal heat generation, that means Qg is equal to 0. The same equation could be written as grad 2t is equal to 1 upon alpha dabba t by dabba t, which is nothing but diffusion equation. So this is a second special case. Now considering third special case, in third special case there will not be internal heat generation, Qg will be 0 and conditions are steady. That means dabba t by dabba t is 0. So what equation becomes is it is only Laplacian operator, so grad 2t is equal to 0, and this is known as Laplace equation. It is a very important equation, and the thing we will see henceforth will be mostly dependent on this, assuming there will not be any internal heat generation and steady states. So these are few special cases that we have seen in this lecture. So for today we will stop here. Thank you.